Hello, I'm creating this video to give you a example problem for cylindrical coordinates when we're doing kinetics. And this problem we started in class, and I wanted to give you the full beginning to end solving of this problem. So what we're going to do is go through 1392 and show the setup and show how we solve to find the forces on the cylinder. So first of all, let's look at the problem. The problem is 1392. And the statement says, using a forked rod, a smooth cylinder C having a mass of 0.5 kilograms is forced to move along the vertical slotted path. Vertical slotted, that's important, so I underline that. R is equal to 0.5 theta, so we're going to start our givens here. We have the radius is equal to 0.5 times theta, and that's in meters, where theta is in radians. If the angular position of the arm is theta equals 0.5 t squared, where t is in seconds, determine the force of the rod on the cylinder and the normal force of the slot on the cylinder at the instant t equals 2. So we're looking for t equals 2. The cylinder is in contact with only one edge of the rod and slot at any instant. So what we're supposed to find, it says determine the force of the rod on the cylinder. I'm just going to call that F. And it also says the normal force of the slot on the cylinder. So we're going to call that N. So F is going to be the force of the rod on the cylinder, that's the forked rod, and N is going to be the normal force of the slot on the cylinder. So our first and most important step here is going to be to set up the problem to make sure we have all of the forces acting in the right direction. So we're going to draw our free body diagram and make sure that we have all our coordinate systems there. So we're going to start off with C. C is just a dot, that's the cylinder that we're looking at. And from C we're going to figure out what our coordinate system is. Well, we see that we have the radius is in terms of theta. That gives you a really good clue that we're going to use cylindrical coordinates. Cylindrical coordinates will help us when we know the radius with respect to theta. So first thing we're going to figure out is the radial direction. Well, the radial direction is just an extension of the radius. The radius goes from the origin to C, and if we extend that out we can draw the radial direction. Radial direction should look something like this, and we're going to call that UR. Okay, that's our radial direction. And of course we know our theta direction has to be perpendicular to our radial direction, and it's going to be in the direction of increasing theta. So we're going to put it right here. So we have our UR and we have our U theta. Okay, so we don't have any forces on there yet, but we do have our coordinate system. So we're going to go ahead and put some forces on there. Forces are going to be in blue. And it says that there's two forces. There's going to be one force acting from the rod, on the forked rod, onto the cylinder. Now you can look at that forked rod and you can see that it extends in the radial direction. And the force from the forked rod on the cylinder is going to be perpendicular to that surface of the rod. Just like any normal force. We know that the normal force of a surface, a contact support, is going to be normal to the surface that's acting on it. In this case, the surface is right here. It's the front surface of this forked rod. That surface is going to be pushing perpendicular to it, so we're going to draw a force that's perpendicular to the radial. Perpendicular to the radial, we know that's in the theta direction. So that's our first force, and that's the force of the rod and the cylinder, so we're going to call that F. Okay, our second force we know is going to be from the slot. Now just like I said previously, the slot, I'm going to erase that first one, the slot is going to contact that cylinder, and the normal force of that slot on the cylinder is going to be perpendicular to the surface of that slot. Now the slot is the path of the cylinder. You can see that the cylinder is traveling along this slot. That's the path of it. So we know that the velocity along the path is always in the tangent direction. So along the path is the tangent direction. Perpendicular to the path is perpendicular to tangent, which we know is going to be the normal direction. So what we're going to do is we're going to draw in that normal force. If I draw it up here, first off, it's going to look something like that. It's not going to be right along the fork, it's going to be perpendicular instead to the slotted path. So we're going to draw it in to look like this. And just like we said, that's perpendicular to the tangential direction, so that means it's going to be the normal direction. So we'll go ahead and draw that in as our normal coordinate, and I'll do that in orange. So this is our UN. Okay, well, we know we're going to need our UT, which is going to be perpendicular to our UN. So our UT perpendicular to our UN is going to look something like that. And I just drew that in perpendicular. That's going to be tangent to the path. You can see that those line up pretty well. So we now have our normal, our tangential, our radial, and our theta directions. Of course, there's one more force acting on this. And this goes right back to the vertically slotted path. The vertical slotted path tells us that this path is upright, meaning the sky is this way. And the ground is this way. If the sky is that way and the ground is that way, that tells us which way gravity will be acting. And of course, gravity will act along with the mass to create a force, which is weight. So we have to put that force on there, and it's going to be acting straight down. And that's going to be the weight of the cylinder. I forgot to label this force. This is our normal force of the slot acting on the cylinder. Okay, so the weight is acting downwards, and that's our typical rectangular coordinates there. So our rectangular coordinates, I'll go ahead and do in red. This I'll call negative y, just to keep the picture a little cleaner. We're not going to put a positive y-axis. So that's our negative y-axis, and that's the way that our weight would be pushing. And then we know that our horizontal component is going to be the x. Looks something like that. So now we have all three sets of coordinates. We've got the rectangular xy, we've got the cylindrical, and we've got the normal tangential. And we also have our three forces acting on that cylinder. So it's really important to look and see if it's vertically slotted or if it's a horizontal path. If it's a horizontal path, then the weight would be acting into the page. If the weight is acting into the page, it's not going to affect our calculations in the xy plane here. It would only affect our calculations if we were including acceleration in or out of the page. If this path is on the plane of the page, then there's no acceleration in or out of the path. So you would just have the weight acting downwards, and of course a normal force counteracting that. But those would not affect our calculations for this problem. That would be if it was horizontally slotted, and that would change your equations. Okay, so now in order to solve this, we're going to need to set up some angles between the different coordinate systems, because we need to be able to relate these forces to the cylindrical coordinate system so that we can sum the forces in the radial and the theta directions. So the equations of motion that we're going to be using, we're going to say that we want the sum, that's the positive radial direction, and we want the sum of all the forces in the radial direction. We know that they're going to be equal to mass times acceleration in the radial direction. Then of course we have the theta direction, and we need the sum of all the forces in the theta direction equal mass times acceleration in the theta direction. We will be able to find our radial and our theta acceleration using the equations that we used previously in kinematics to find the radial and acceleration in the theta direction. However, to find all of our forces in the radial and the theta directions, we're going to need to know the angles that relate these different coordinate systems. So the first angle we're going to look at is psi. We learned about psi in this last chapter, and psi is always between the radial and the tangential coordinate system. And the equation for psi is the tangent of psi is equal to a radius over dr d theta. So right there we will be able to relate our radial and our tangential directions. Okay, and there's one other angle we need, and that angle is going to help us relate our weight to our radial and theta directions. And the one we need for that is actually theta itself. Now theta is on the drawing, so all we need to do is transfer theta on this drawing down to our coordinate system. So theta goes from the horizontal to the UR direction. So we're just going to add our theta, which is going to go from the radial to the UR direction. That's our theta. Okay, so we have two angles there, and we know how to find them. Let's go ahead and find psi to start off with. So to find psi, our radius is going to be equal to 0.5 theta meters. We also know that theta is equal to 0.5 t squared. And we know at the instant we're looking, t is equal to 2 seconds. So you can plug theta into your r equation, and you get r is equal to 0.5 times theta, where theta is 0.5 t squared. So that's equal to 0.25 t squared. To figure out what our radius is at t equals 2, we just plug in 2 for the t, and we get the radius at 2 is equal to 0.25 times 2 squared, which is equal to 1 meter. So now the radius is equal to 1 meter at t equals 2 seconds. So that'll be the top of this equation here. That's going to be equal to 1. Now we just need to find dr d theta, and that's pretty simple because we have r is equal to 0.5 theta. You take the derivative of that equation with respect to theta, you're going to get r dr d theta equals 0.5. Okay, so now all we have to do is find our psi angle, and we're just going to use this equation right here. We'll say the tangent of psi is equal to r, which we just determined was 1 meter. We have 1 meter over the top of dr d theta, which is 0.5 meters. Meters cancel out, and we get tangent of psi equals 2. Take the inverse tangent. Psi is equal to the inverse tangent of 2. And you can plug that into your calculator, and you get that psi is equal to 63.43 degrees. Okay, so we found psi. I'm going to go ahead and put that on our drawing up here. We get 63.43 is what our psi angle is. And now I'm going to erase some of this to get a little bit more room, so if you need to copy any of it down, just go ahead and hit pause. Okay, and there's one more angle we need, which of course is theta. So we will just say theta is equal to 0.5 t squared. Theta at 2 seconds, which is the instant we're looking at, is equal to 0.5 times 2 squared. So theta at 2 seconds is equal to 2 radians. Okay, we have both the angles that we need then. And we can write here that theta is equal to 2 radians. And if you like, you can convert that 2 radians to degrees. So the theta at 2 in degrees is 114.59 degrees. Okay, now that we have the angles, we're going to jump into our equations of motion. So I'm just going to rewrite the equations here. We had a positive direction that way for UR, and we have the sum of the forces in the R direction equal mass times acceleration in the R direction. So we need to figure out what the forces are in the R direction. So first of all, if we look at the F force, the force of the rod on the cylinder, that force is in the theta direction, so that's perpendicular to the R direction, so we're not going to have any force in that. So the other two forces, we need to take the components of them. And to figure out what those other two forces are, we have our psi angle, which is 63.4 degrees. Now we know that our normal direction is going to be perpendicular to our tangent direction. That tells us that the angle between the normal and the tangential axes is 90 degrees. So we can find this angle right here. That angle is just going to be 90 minus psi. This angle is 90 minus our psi. So the value of that angle that we get is just 90 minus 63.43, and that would be equal to 26.57 degrees. So if we want to find the component of the normal force that's acting in the r direction, you can see it's going to be negative. That component of the normal force acting in the r direction is just going to be the normal force times the cosine of this angle we found, 26.57 degrees, and of course it's going to be negative in the UR direction. Now we just need one more force in the UR direction, and that's W. So we need to figure out what the angle is for W. Okay, so all I did is I extended the UR axis down. And the reason I did that is because we know that theta is 114.59 degrees. We know that a straight line has 180 degrees. So we can find the angle right here. This angle is going to be 180 minus 114.59. Okay, and what I get for that is 65.41. We also know that the x and y directions are 90 degrees apart, so that allows us to find this angle, which would just simply be 90 degrees minus the 65.41. And that ends up being 24.59 degrees. So I'm going to erase some of this just to make the drawing a little neater, because there's been a lot of angles on here. Okay, with that 24.59 degrees, we can go ahead and figure out what the component of the weight is going the radial direction. Looks like it's going to be negative, and we can say that's negative weight of our cylinder times the cosine of 24.59 degrees. And all of that's going to equal mass times acceleration in the radial direction. Okay, so now we're going to move on to the theta direction and do the same thing. So we have the theta direction positive down this way. Sum of the forces in the theta direction we know is going to be equal to the mass times acceleration in the theta direction. We already have our angle, so we just need to figure out what forces are in the theta direction. Of course, looking at it, we have the force of the forked rod on the cylinder is in the theta direction, so we're going to get that full force, and that's in the positive theta direction. So we have that full force, and then of course we're going to have the normal force, and we have to figure out which direction that's going in. It looks like that's also going to be the positive theta direction, and it's going to be the sine of the normal force. So the normal force times the sine of 26.57, and then the weight's also going in the positive normal direction, or positive theta direction, and we're going to add the weight, and that of course is going to be the sine of 24.59 degrees. All of that together is going to be equal to mass times acceleration in the theta direction. So now we have our equations of motion put together with all of the forces that need to be in those equations of motion. The next step is we need to figure out what our AR and our A theta is. Luckily we know how to do this through kinematics, because we've done this before with cylindrical coordinates. So we need to write out our equations for AR and A theta. We know that the acceleration in the radial direction is equal to dr dt minus r times d theta dt squared. So let's do that real quick. Dr dt, well, our r is 0.5 theta and our theta is 0.5 t squared. So our r is equal to 0.5 times 0.5 t squared, which is equal to 0.25 t squared, Therefore dr dt, just take the time-based derivative of that, the 2 comes down, and we get 0.5 t. So dr dt is equal to 0.5 t. We're also going to need the second derivative of r with respect to time for the theta direction, so we might as well find that now. Second derivative of r with respect to time is going to be equal to the time-based derivative of that, which is simply 0.5. Okay, and let's do our thetas as well. So we know that theta is equal to 0.5 t squared. D theta dt is going to be equal to t, and the second derivative of theta with respect to time is just going to be equal to 1. Okay, so now we're going to calculate AR and A theta. AR, as we wrote above, is equal to dr dt minus r d theta dt squared. Plug in values for that. Dr dt is 0.5 t. Now t is 2, so 0.5 times 2 is 1. So our dr dt is currently 1. Minus our r is also 1. We have that written right up here where we solved for it earlier. So 1 minus 1 times d theta dt is t, and since t is 2 at this instant, we're going to plug in 2 for that, so it's 2 squared. So we get 1 minus 4 and right here I can see that I made a mistake. Hopefully you caught my mistake as you were following along. My mistake was I wrote down the wrong equation for the acceleration in the radial direction. Acceleration in the radial direction is not the first derivative of r with respect to time, it should be the second. So, check the book, make sure that my equation's right, and we get that it should be the second derivative of r with respect to time squared. Also down here, this should be the second derivative of r with respect to time squared. And we know that that is 0.5. We already solved for it over here. So we're just going to change this 1 and make it 0.5. And we get 0.5 minus 4, which is going to be negative 3.5. That's going to be meters per second squared. It's easy to find that mistake because the second derivative of r with respect to time would be meters per second squared, whereas the first derivative of r with respect to time would be meters per second. So our units would not match. Okay, so we have the acceleration in the r direction is negative 3.5 meters per second squared. Let's do the theta direction. Our equation for the acceleration in the theta direction is r times the second derivative of theta with respect to time squared. You can see our units line up there, plus 2 times dr dt d theta dt. And once again, we have the units of meters per second squared, so everything lines up. So I know I didn't make a mistake on that one. So our r is currently 1, so it's going to be 1. Second derivative of theta with respect to time is also 1, so 1 times 1 plus 2 times the first derivative of r with respect to time, which is 0.5 t. T is 2, so if we plug that in, we also get 1. And d theta dt is t, which in this case is 2. So we get 1 plus 4. The acceleration in the theta direction should be 5 meters per second squared. Alright, well again I need some room, so I'm going to clean this up a little so that we can use this information to solve our equations of motion. So if you need to copy anything down, go ahead and pause it real quick and get it copied down. What I'm going to erase is the calculations we did for the radius, dr dt and d theta dt. Okay, there we go. I got a little bit more room. And what we're going to do now is just solve our equations. So the first equation, sum of the forces in the r direction, we have negative n times the cosine of 26.57 degrees minus w times the cosine of 24.59 degrees equals mass times acceleration in the radial direction, which in this case is negative 3.5 meters per second squared. The second equation that we have is going to be our force, which is one that we need to solve for, plus n times the sine of 26.57 plus our weight times the sine of 24.59, and that's going to be equal to our mass times the acceleration in the theta direction, which we just solved for, which is 5. So you can see, if you look at this carefully, we have two equations and two unknowns, so we should be good to go. What are our two unknowns? Well, they're the two we're supposed to be solving for. There's the normal force of the slot on the cylinder and the force of the rod on the cylinder. Those are unknowns. W here we can find because we know the, we're given the mass of the cylinder is 0.5 kilograms. I didn't write that in my given, that was a mistake. So mass is equal to 0.5 kilograms. So we can use that to get the weight. So we're just going to say the weight is equal to mass times gravity, which is equal to 0.5 times 9.81 meters per second squared. And we get 4.905 newtons. So W is equal to 4.905 newtons. So we have two equations and two unknowns. We can solve this by substitution, or we can solve simultaneous equations in a matrix. I'm going to go ahead and use the matrix just because I think it's a little bit easier. So we just need to rearrange this so that it looks in the form ax equals b. And of course I need a little bit of room again, so I'm going to erase my acceleration in the r and acceleration in theta equations. And actually I changed my mind. Since we have one equation that only has one unknown, some of the force in the r direction, we're just going to solve for that directly. So I have this equation right here. I can go ahead and solve for n, and I'm going to put n on the other side to get rid of my negative sign, so I get n times the cosine of 26.57 degrees is equal to negative w, which is 4.905 newtons, times the cosine of 24.59, and then I'm going to subtract mass times the acceleration in the radial direction. And we can even plug in the mass there. That mass is 0.5 kilograms. So this is just a calculator exercise at this point. N is equal to negative 4.905 cosine of 24.59 plus 0.5 times 3.5. You can see I had two negatives there, so I made a positive. Divide the whole thing by the cosine of 26.57. Okay, plug that into my calculator and I get negative 3.03 newtons. Okay, if you happen to be looking at a solutions manual and you saw that it was a positive 3.03, that's just because the free body diagram is drawn differently. I drew my normal force as if the normal force is coming down from the top of the slot. That was an assumption I was making. I was saying that the cylinder was going fast enough so it was overcoming its weight and therefore hitting the top of the slot. I was incorrect. As you can see here, I got a negative number, which means the normal force is actually going in the opposite direction and it's pushing up on the cylinder. So that's a correct answer. The normal force is going up, and how you'd write your answer is the normal force is equal to 3.03 newtons, and that would be going in the positive r direction, that way, which is opposite from the free body diagram that I drew. I'm sorry, and I said positive r direction. I actually meant the positive normal direction. which is perpendicular to motion. Okay, once again, it's time for me to clean up a little bit here so I can have more room to solve for F. So I'm going to do that. So if you need to copy anything down, go ahead and hit pause. Okay, I've got a little bit more room here, and now I can just solve the second equation. I'm going to solve for F. Let me get blue ink here. F is equal to, just solving the equation right above, it's going to be equal to negative n times the sine of 26.57 minus w times the sine of 24.59 plus the mass times 5 meters per second squared. We know all of those values, so we can plug them in. So F is equal to negative. And now you can see here we have our normal force. It's important to plug in the negative number that we solved for, because that was in the direction that we used, the direction of the free body diagram, to create this equation of motion. So we have to stay consistent. If we drew the arrow going downwards, we get a negative number. We need to plug in a negative number here. Times the sine of 26.57 minus the weight, which we solved for was 4.905 newtons, and that's times the sine of 24.59 plus the mass, which is 0.5 kilograms, times 5 meters per second squared. All of our units are in newtons, so it's working out there. Now we just need to plug into our calculator. And when you solve for that in your calculator, you end up getting 1.81 newtons, and that's in the positive direction, so that means we drew the force in the correct direction. In this case it was pretty obvious because we knew which direction the fork was moving. So there's our answer. We have the force of the rod on the cylinder is 1.8 newtons. The normal force of the slot on the cylinder is 3.03 newtons. The force of the rod on the cylinder is positive theta direction. The normal force of the slot on the cylinder is the positive normal direction. Let me know if you have any questions about this. I hope it was helpful.